Hello there, my name is David Cater. In this video, we're going to take a look at some basic principles of a parallel RLC circuit. What we're going to do first, though, is just look at pure circuits. So that means a purely resistive circuit in parallel, a purely inductive circuit, and then a purely capacitive circuit. Once we learn these basics, we can then go ahead and start to mix the values R's with L's with C's in a parallel circuit. All right, so a couple of things, very basic. What we want to understand is the voltage across each component is going to equal the source voltage. So we could say that the E total is equal to the E or the V of R1, which is equal to the V of R2, etc., etc., etc. So the voltage across everything will be the same. Same thing here. The voltage E total is going to equal the V of L1, which is going to equal the V of L2. And the voltage across the inductors are going to be the same, and we can make the same statement. The E total is equal to the V of the cap 1 equal to the V of the cap 2, etc., throughout these circuits. That's the thing about the parallel circuit, of course, is voltage is constant across each of the branches. Now, with that being said, then what we want to be looking at is more in terms of power and current. So when we're looking at a circuit like this, current is going to flow into this branch, and it's going to flow into this branch, and then once again flow into the third branch here. So there's going to be current coming from the source going into each branch. So what we want to do then is add up our total current. So for this resistive circuit here, we can say I total is equal to the I of R1 plus the I of R2 plus the I of R3. So we have to add up each of the currents in each branch to get the I total that's coming from the source. All right, so it's sort of a basic circuit property that we can remember from before, but there's a reason why we can just simply add the currents up. All right, so what I'm going to do is plot out my two values that we want to be looking at. All right, so I've got my voltage, my E total here is going to be my reference. Okay, voltage is constant across each component, so we might as well make voltage the reference. And then when I plot out the currents on my phasor diagram, we know that the current is in phase with the voltage with a resistive circuit. So my currents are all in phase with each other. So I can add all three up to get to my I total because they're in phase with each other. So technically I added them up as phasors, but I kind of didn't have to do any trig because they're all at 0 degrees. All right, so that's true with the resistors. In a purely resistive circuit, we can add all the currents up that are resistive currents. Moving on to the inductors, voltage is the same, but the same principle applies. Current will flow into that branch. We add another inductor, more current is going to flow from the source into this branch, and then more current will flow from this branch. All right, so we can do a very similar thing. We can say I total is going to be the I of inductor 1 plus the I of inductor 2 plus the I of inductor 3. All right, but once again, we have to make sure that we're respecting the phase displacement between everything. So I'll go ahead and I'll plot the phasor. So that's my E total here, pardon me, and my I total. In an inductor, current is going to lag. So my I total is going to go down here. All right, so once again, because all of my currents are in phase with each other, L1, L2, L3, and then I total, well, I can simply just add them together without having to do any trig once again, but only because they're in phase with each other and they're directly added together as an out of phase current, all right? And this, of course, we must respect the 90-degree lag in a pure inductor. Once we start to add resistance here, that'll shift off of 90, all right? And so that's at 270 or negative 90, but it's a 90-degree lag. The last one is the cap, and same thing applies. We can just simply figure out, okay, the current that charges onto that plate and the current that charges onto this plate and onto this plate, we can add those currents together. We can make the same statement. I total is the I of cap 1 plus the I of cap 2 plus the I of cap 3. And that's the exact same thing as before. Well, if our E total is our reference, our current is leading in a cap, so our currents are going to be all up at 90 degrees here. And so as a result, we can go ahead and add our currents directly with their numerical values and not have to do trig. All right, so this is only true for circuits that are so purely resistive, so adding resistive currents to resistive currents, inductive currents to inductive currents, and then capacitive currents to capacitive currents. All right, so when we start to mix L's and C's, or R's and L's, that's when we really have to start to pay attention to the phase of each of the components, all right? So in the next video, we'll start to mix R's and L's, and we'll see what happens. So see you in the next one.